So, yeah, the determinant of the inverse of any matrix could be written in terms of its cofactors. Now, for all the elements of a matrix, such that those elements are all functions of a variable, parameter, whatever, x, say, we could find the derivative, or the derivative of the determinant of a matrix. The determinant of a matrix, of course, is expanded in this form usually, where for some I row, we could expand this along some column J. Now, the cofactors, of course, we have stated is defined as that. When we differentiate the determinant of a matrix with respect to x, of which the elements of the matrix itself are dependent on x, now we will write it in this form. Here, of course, whereby we know that from the derivative of the determinant of a matrix, we can obtain just this, or equal to the cofactor down. Now, given the matrix in this form, we could either decide to choose this to be equal to this, from this to be equal to that, or we could also consider rewriting this derivative, that's this formula here. We could consider writing this formula as this derivative of the determinant of the matrix with respect to a sub ij. Of course, in that case, we'll be done or be gone with this dx, and then what we'll be left with is just this as the coefficient, which we have shown to be equal to the cofactor this, or the same as that. By the way, right from the beginning, we have also written that the cofactor will also be written as this. So as a final result, we have that the derivative of the determinant of a matrix with respect to its element is equal to the inverse of that matrix times the determinant of that matrix. Why is all this so important? Because it will help us in the analysis that we shall be performing in general theory of relativity. Now, for instance, the determinant of the metric tensor, we could call that G. If we were to differentiate that determinant with respect to the elements of the matrix tensor, we will very simply obtain this, the inverse of the matrix times the determinant of the matrix, which we already named G. And the inverse of this G sub alpha beta is G superscript alpha beta. Now, of course, this is a standard result. We could try to perform the same operation for the determinant of, say, for instance, let me clean this so we have some space. We could try, for instance, say, to perform the derivative of the determinant alpha beta. Now, in the process, with a very simple operation, not too much of a big deal, you come to this, which will also be written as this. Just reading just the same formula from here. The inverse of G alpha beta, determinant of G alpha beta. The inverse of this, of course, as usual, is that, and G sub alpha beta is that. They are the determinant of that. So in essence, we will end up with this formula. For this case, the determinant of G with respect to G alpha beta superscript will give us minus G sub alpha beta. Now, the determinant of the derivative of the determinant G with respect to G sub alpha beta will give us G, then alpha beta superscript. You can take note here, there's a minus sign which is absent here. And here we have alpha beta superscript here, or we can call them covariant indices and contravariant indices here. Okay, now this is important because we could use it to show, for instance, the variation of this. Y minus G raised to power half is something we are going to be using to define the density of vectors and tensors. For instance, you have a vector A alpha. The density of this vector is minus G raised to power that A alpha. And usually in operations, we usually perform the variations of variables. So we want to know how to deal with the variation of such things as that. Now, let's perform the very simple one. For instance, if we want to perform the variation of minus G 1 over 2 here, this, of course, we have demonstrated succinctly as that, the G sub alpha beta, and here G sub alpha beta. Of course, this is the same thing as this, minus G, and here the G, now the G sub alpha beta, and then I have variation of G sub alpha beta. Okay, now in this case, of course, we know what this could give us. This is the same thing as some minus half. Here, I have times of minus g raised to power minus half. And then also, we are going to be left here with the product that we have already shown from matrices. So this is going to give us G superscript or contravariant indices. And that is what we have. Now this is same thing as minus 1 all over 2 dot 1 over the square root of minus G. And then I could perform some sort of rationalization. Minus G here. So I have G superscript alpha beta and this alpha beta. And of course, from this we can see that it's easy to have minus 1 all over 2. These two multiply themselves. And I have here with me minus G and then minus G due to these two. But I have another G here, G alpha beta, G sub alpha beta. Now this minus goes with this and this goes with that. And of course, eventually we can see that this gives us 1 all over 2 square root of minus G alpha beta, and that's alpha beta. Of course, the same could be performed for this case, in which case we will have to perform such a variation as this, minus G raised to power half. But then in this case, we are going to say minus G half, but the G alpha beta on top, and then the variation will be that of alpha beta. In a very simple step, and with the help of this formula, we could at the same time show that the variation of minus G could also be written as this. Actually, this is very tricky. So you can see the only big differences we have here: contravariant indices and the variation of the covariant indices, whereas it's reversed in this other expression, but then with the minus sign that comes with this. Okay, so let's move on to the next set of